In this video, we're going to do something completely different. It's time for story time! This is Isaac. Isaac is happy because he just turned 16 and he just got a car. It's a really nice car. It's a Porsche brick. Isaac wants to take his new Porsche brick on a joyride, which you should never do, and see how fast his car can actually go, which you should also never do. So Isaac drives out to the middle of nowhere, otherwise known as Oklahoma. And in the state of Oklahoma, there's this very special road. It's called the Oklahoma Turnpike. That's probably not where it is, but hey, let's pretend that's where it is. The Oklahoma Turnpike is a toll road, which means that there are toll booths. Specifically, there's one here at point A, and there's also another one here at point B. And when Isaac goes through these toll roads, he'll be told the standard amount, and there will also be a timestamp placed on his toll receipt. Now, the Oklahoma Turnpike is known for joyriding, mainly because I think its speed limit is somewhere around 75 miles per hour. That's pretty exciting. Unfortunately, the police also know this, and so they sit out with their cruisers at the toll points A and B. So Isaac knows this, so he's going to be very, very careful when he drives through just the toll plazas, because he knows that the police are hiding there with their laser scanner detectors waiting to trap him. So when Isaac comes along in his green Porsche brick, there it is, he's going to be very careful to be driving the speed limit of 75 miles per hour when he enters the turnpike, and when he leaves the turnpike at point B. He's also going to be very careful and driving the speed limit, which you should always do, at 75 miles per hour. And so Isaac thinks that he's pretty clever, because he says to himself, well, if I drive 75 miles an hour through Toll Plaza A and the police don't catch me there, then I can drive as fast as I want on the rest of the turnpike, because there aren't any police there, and then I can slow down and drive through Toll Plaza B at 75 miles an hour, and this police car isn't going to do anything because he's just like drinking coffee and eating donuts, and yup, another person going 75, better eat some more donuts. And so Isaac thinks that he's pretty clever. And so Isaac thinks that he's going to get away from this experience without having broken any laws, or actually he has, because he's been speeding here, because he hasn't been going 75, because he's been trying to max out his car, which you should never do. And so he feels like he's going to get away from this experience without being caught. Unfortunately, as the story goes, a couple weeks later in the mail, he gets a ticket, and he's got to pay his ticket. And so he's confused because, well, I didn't get caught by the police, so what's going on? Well, let's think about this for a second. Let's graph Isaac's trip. So on the x-axis, we'll have time. And so Isaac went through Toll Plaza A. The toll plazas are going to be on the y-axis, so we have Toll Plaza A and B. And so let's say that Isaac went through Toll Plaza A at 12 o'clock noon. And he finished his joyride at 2 o'clock in the afternoon and got to Toll Plaza B. And the total distance of this turnpike turns out to be 180, no, let's call it 200 miles. It's a 200-mile long stretch of road between A and B. Well, we don't quite, we know that he was going 65 miles an hour at both the beginning and the end, so we can draw in slopes, because remember, slope is the rate of change of distance over time. It's the derivative of distance over time, which is the slope. So we know how fast he was going at the beginning and the end, but we don't quite know how fast he was going at every point along his trip, but that's okay. So let's do a little bit of math and thinking. Well, he went 200 miles, and it took him 2 hours? So his average speed was 100 miles per hour. So the question is, do you think that he ever went 100 miles an hour? So think about it. Hopefully you've thought about it for a little bit. And the answer is, well, maybe. Yeah, probably. Like, it makes sense, right? It makes sense that if his average speed is 100 miles an hour, but he was only going 65 here and 65 here. That somewhere in between points A and B he had to have been going at least 100 miles an hour to get that average speed above the 65. Unfortunately, Isaac isn't so bright, so he has to take it to his brighter friend, or his smarter older friend, Gottfried. And Gottfried, he's a pretty cool dude, because he took calculus last year, and so he tells his friend Isaac that, hey, you need to know something that's called the mean value theorem. And the mean value theorem is very important to calculus, but it also is something that makes sense. Being all book smart and stuff, Gottfried describes the mean value theorem as this. If f is continuous on the closed interval from a to b, and f is differentiable on the open interval from a to b, then there has to be some x value, we'll call it c, and c is between a and b, such that, wait for it, f prime of c has to be equal to f of b minus f of a, all divided by b minus a. Isaac is confused because he's like, that doesn't help me at all, bro. You just told me a bunch of math stuff and I'm trying to figure out why I got a ticket. Well, Gottfried explains to him that the function that described Isaac's motion satisfied these two conditions. First of all, the car's position was continuous because it didn't disappear somewhere and reappear somewhere else. Like if we look at our graph, the car couldn't have gone this far, disappeared here, and then reappeared here and kept going, right? I know a Porsche is cool, but they're not like magical like that. Gottfried also tells Isaac that the function of his car is also differentiable because essentially the speed at which you're traveling is smooth. Like the rate of change of position over like your position is smooth. You don't just suddenly like reverse and make a really sharp turn all of a sudden. So it is differentiable between the two times that he was traveling. Isaac's like, yeah, okay, I guess I get that part. Gottfried says, great, let's work on the nitty-gritty stuff. That means this stuff here. We'll take this one thing at a time. First off, there's this thing here on the right-hand side of the equation, and that looks like the difference in two y values divided by the difference in two x values. Notice that this is not the derivative because it doesn't have the limit, but this is a slope. And as you recall, a slope is an average rate of change. And so let's calculate this using the data that Isaac had. F of b and f of a are the two y values at the times b and a. So let's figure out the interval. Well, the interval that we were working with was from 12 o'clock to 2 o'clock. Okay, so the position at 12 o'clock, we said that was 200 miles, because that's what the final distance was. And the position at 12 o'clock was, keep in mind that I switched these, so this is A and this is B. So the initial position was 0, because that's where he started. And then the total time is the difference between 2 o'clock to 12 o'clock, which is 2 minus 0 hours. This is where we get that original 100 miles per hour from. Think back here, that's where that 100 miles per hour came from. And so the blue line represents the average rate of change between the 2 points. So in blue, I'll label this average rate of change. Notice one thing more, that because we're taking the slope, oops, I don't want red, I want blue. Notice also that because we're taking the slopes between two distinct points, that this average rate of change is the slope of the secant line, because it goes between 2 points and not just one, like the tangent line. Isaac's like, okay, I guess I get the fact that my average rate of change was, in fact, 100 miles an hour because that was my total distance divided by my total time. That still doesn't explain to me why they know that I was going at least 100 miles an hour, or exactly 100 miles an hour, at any given moment. Gottfried explains, well, that's where this other side of the equation comes in, the f prime of c. Remember from my definition that c had to be in between a and b. So on our picture here, C could be any time between 12 and 2 o'clock. Let's put it here. Now, the mean value theorem doesn't say exactly where it is. All it says is just somewhere it exists. So maybe it's not there. We'll actually do it when we draw it. But the point of this is that we're finding f prime of c. Remember that prime means derivative, and derivative is the instantaneous rate of change. And so Gottfried continues to explain to Isaac that, hey, because of this theorem, your instantaneous rate of change had to have been equal to 100 miles an hour, your average rate of change at some point between A and B, which is some point between 12 and 2 o'clock. And Isaac's like, fine, I get it. That's okay with me. Isaac might be content, you might not be. So let's take a look again at this graph. So keep in mind that the position function was not only continuous, but it was also differentiable. So I couldn't draw a function like this where I have a sharp turn. Like, I can't have anything like that. So the trick is to try to draw a function between here and point B that doesn't have any function that you draw. Let's say I draw this function. Any function that you draw will have at least one point where the slope of the tangent line here, and also here, the slope of the tangent line is parallel or equal to the slope of the secant line. And remember that this slope of the tangent line, this is the instantaneous rate of change. And so in words, the mean value theorem says that if a function is continuous and differentiable on some interval, then somewhere between the 2 points, the average rate of change has to equal the instantaneous rate of change. Or you could say that the slope of the secant line has to be equal to the slope of the tangent line, so here and here. Or, more mathematically, this is the definition that is sometimes used in some problems. And this will be used later on when we prove the fundamental theorem of calculus. I'm not going to make you guys prove that, obviously, but this theorem is pivotal in doing that. But basically, this is the theorem that this is the equation and stuff that you'll use when you're actually calculating where this value of c is. And so in the end, Isaac was sad because he had to pay his money to the people because he didn't know calculus. So the point of this lesson, the moral of the story, is that you should know and learn calculus so that you don't get speeding tickets when you plan on joyriding your car. The end.